Right, this is going to be a video about your displacement time graph. So we haven't really talked about displacement time graphs. Basically, this is another way of showing what happens when your object moves and back from the origin or towards the origin. And we're going to look at this in relations to velocity as well. This little app that I have, this is a Java app. It's free online. You can actually go and search this and play around with it because it's really helpful. I use this to teach physics all the time, and this is called a moving man, and it's from PhET, which is P-H-E-T. If you search moving man P-H-E-T, you'll find this. Basically, this kind of relates all your position time graph, your displacement time graph, with velocity and acceleration all in the same screen. So it's like, what would happen if your velocity were to be going this direction? How does that look in an acceleration time graph? And also, how does that look in a position time graph? So to explain this, you can see this man right in the middle. He can move around back and forth. The 0 is the origin. So notice that once I touched it, the time started. So if I were to go move away, you can see that my position starts to go up because I'm moving away from the origin. And if I go back down towards the origin, you can see my position time graph going back to the origin. So right now, just look at the displacement time graph because the velocity and acceleration looks really unclear right now. What you need to know is that if I were to start at the origin, and let's try to do a constant velocity. So let's change this to 2. What would my position time graph be if my velocity were to be 2 meters per second? So let's play this. You notice that my position time graph has a positive slope. So this is your slope. Remember in math you learned about slope. This is basically your position time graph when you're in constant velocity. So if we're jumping ahead a little bit here, is that why is the velocity time graph flat? Well, because this is your velocity. And you're not accelerating, you're moving at the same speed throughout the entire time. So that's why this is from point 0, you're going at 2 meters per second. To this point, you're still going at 2 meters per second. So there's no change in velocity. How does that look in a position time graph? It's a straight line, straight positive slope. So what if we were to change this to a negative velocity? So let's press play. You can go and see that here, once it hits 0, because it's going back towards the origin, the position time graph goes back towards 0. That's your displacement. Remember, displacement is your final position, subtract your initial. So in here right now, where the man is, his final position is 0, subtract where he started, 0, 0. And in your velocity time graph, because it's a constant, steady velocity, this doesn't change. So this is your velocity. So what would it look like if we were to have 0 velocity? He's not moving at all. What would that look like on a position time graph and a velocity? So if we press play, he's just standing still, looking like the man. So you can see right here in velocity time graph, flat at 0 because that's what velocity is. He's not moving, 0. Did he move anywhere in your position time graph? No, he didn't. He stayed at the same spot where he started off with. That's your displacement of 0. So that's your displacement time graph in relation with velocity. So what if we were to sort of accelerate, move quicker for every second or every time that it passes? That's what acceleration is. So if we were to change this into, say, 1 meters per second square, that's my acceleration. Let's see what happens. Oh, let's do a more visual one. 5 meters per second square. Watch the position time graph. So you can see that instead of a straight line, well, he crashed, but instead of a straight line, you can see that this is a curved line that goes up. So when you're accelerating, this goes up faster, and faster. If this were to allow to keep going, this would go up here because that's acceleration. So a couple of things to notice from this graph. Constant velocity, velocity going back to the origin, negative velocity, 0 velocity, acceleration. So what if we were to do negative acceleration, negative 5 now? You can see that instead of going back up, it's going towards the origin because it's negatively accelerating, going back to the origin, and this is accelerating downwards. It's a curved line. So acceleration is a curved line, constant, no acceleration, constant velocity, straight line. So going back to our notes, this is something to look at. So I'm going to give you the descriptions right now, so take it up. So check it out right now. So since we have our different graphs, I'm going to show you all the variations that you can write down to make sense out of the graphs. Again, this is displacement time graph, so anytime you're graphing this, you're going to have your time and you're going to have your displacement, so d. Sometimes it could be written as x. So what does a displacement time graph look like when you have a constant velocity? So keyword here is constant. That means a steady speed. And I don't want to use speed and velocity too much because speed is actually a scalar while velocity is a vector with a direction. But to give you an idea what a velocity time graph is that since it's constant, if you remember from the previous video, your line is going to be a straight positive slope line. Okay, so this is your displacement time graph on a steady velocity. And the description here is, I wonder if I can type it in. I can. So let me just type this in. This is, you have, the description of the graph is that there is a steady positive slope. That's what the description is for a constant velocity over time, because you're basically moving away from the origin at the constant rate. And then now, if we look at the second one, zero velocity over time, if you remember from that activity or that demonstration, again, this is a displacement time graph, so I have my d and I have a t. Because you have zero velocity, you're not going to move. So you're just going to stay at the same place and not moving. So you can have a straight line down here. Can you have a straight line anywhere else? Yeah, you can. So it doesn't have to be at the origin. What if you stop somewhere later on and you just stop moving? That's possible as well. So you can be up here, as long as it's a straight flat line, that is zero velocity, because this, from this point in time to that point in time, you haven't moved at all. That means you haven't traveled. So that's zero velocity. So the description of the graph is that there is a flat line to represent zero velocity. Oh, typo. So that's what that is. Let me see if I can move this over so you can see. So that's the description for zero velocity. Okay. And then you can also have a negative velocity. So if we were to go and look at something with a negative velocity, what does it look like if this were to going down that way? So what does that line represent? This is a negative slope towards the origin. So that's what that means. What the origin means is that where you started off. So remember, these are all slopes. These little diagonal lines, they're straight, so they're slopes. So because this is going back towards the origin, you are moving. There is a velocity. It just means that you're moving towards back where you started. You can actually go past it. That's okay as well. So three different ones. You have a positive one that has a steady constant speed. That's away from the origin. And if you have zero velocity, it's just a flat line. If you're going back towards the origin, that's going a negative slope. So this is a negative slope. So slopes are your diagonal lines. So let's look at the next couple ones. Slow movement and then rapid movement. So if we were to look at the PhET, this one, basically the slow movement could be this, and then remember acceleration is that. And if we wanted to look at this again, let's try this. Slow movement to velocity. Okay, that's my precision time graph. What if I were to change it to 10? A lot faster. Bang. So you notice that at this point it has a steeper slope, more vertical. That's your steeper. That means you're traveling faster. So here, if I were to write this down, if I were to do a precision time graph, here's my T and my D. Slow movement could be a very steady, and a rapid movement can be very, oh, that's way too fast, like that. So this is your slow, and this is your rapid, because you just went from slow to fast. So it starts off, the faster the velocity, the steeper the slope. That's what that means. Okay? So that's slow movement, then rapid movement. And if we were to go the next graph, moving backwards, then forwards, displacement time graph right here. If we're moving backwards, remember, anytime you're moving backwards towards the origin, it's always like this. And if you change into forwards again, it's moving away from origin. So this is towards origin. And then this is away from origin. So that's the thing. And remember, this is a steady straight line, a slope. That's going to be a steady velocity. So let's see. The description for this is towards origin and negative slope, and then away from origin is your positive slope. So away from origin, positive slope. Okay, so that's moving backwards and then forwards. The last one is a little bit tricky because it's a yo-yo oscillating up and down. So what oscillating means, stop. If you have a yo-yo, remember here's, let's see, here's your hand. That's not really a hand. Let me draw this again. Here's your hand. Well, it's hard to draw on this. And yo-yo goes down and comes back up and then goes back down, up and down. So what do you think your displacement time graph is? So let's look at with that Java app and see what the moving man would say. So let me reset all of this. So if I were to go, basically oscillate is going back and forth, back and forth. So check out what happens to the position time graph. So I'm going to go back up here and back down and back up and back down and back up, back down. If I do it fast, the steeper it is. Okay, if I do it really fast, it's super steep. If I do it really slow, it's not very steep, right? So you can see that as it oscillates, the lines basically, it looks like one of those EKGs going up and down, like your heart monitor. So in a yo-yo that's oscillating, we notice that this is going to go away from origin, comes back towards origin, goes up, back down, and up and down, like a bunch of mountain peaks. So you can see you have up and down peaks. That's your yo-yo oscillating up and down. So that's your displacement time graph. And try to understand what is actually happening and visualizing with the graph. That's really important because when you're just memorizing this, you might not have a full grasp on the meaning of why this graph is like this or that. Okay, so try to understand that you're basically plotting displacement and time together. So just picture yourself moving as a moving man. What happens when you move away from origin? What happens when you move back to the origin? What happens when you're running? Compare if you're just kind of slowly walking. Once you can understand that, your velocity and acceleration time graphs are actually pretty straightforward. So hopefully this video helped you in understanding your understanding of your displacement time graph. And if you are really interested in strengthening your understanding, go check this Moving Man app because it's actually pretty fun to watch this guy. So if I want to go and do like 20 meters per second, look how fast he runs, and he crashes into the wall. Sometimes like you can take this wall out, and then well, since he's over there, let's do like -50. Bam! See how steep that is because he was running super fast. So this is a fun little app for you to try it out. So that's your Moving Man, and that's your displacement time graph.